You know what? Instead of doing that problem, let me see if I can find one in the book. And just do. Okay, let's see. Taking a long time. Let's see if my battery goes down or up. Staying at 6%. Okay, so that's what we want to keep. So we'll get rid of all the others. Okay, go away. Come on. Where is it? Okay, so I'm going to find a problem in the book that's kind of like the one that I was working on. Oh, he has one. Let's find him more. Since there's one already, we'll find another one down here. Let's see. Do we want to do that one or do I want to do? Oh, there's one. But then there's one, and then there's one. Ooh, that one has the most complex. Okay, so we'll do that one. I'm trying to find one that is the most complex. Oh no, I have the wrong kind of. Okay, it's okay. There we go. We'll just go ahead and go down to a new page. Yep. And we'll listen to. That's the one. Not there. Not there. But there. Okay. So let's see what he said. I don't. Here we go. We'll do. Uh, there's the problem statement. So it says two disks, A and B, have initial velocities that are shown right there and there. If they have a masses of 4 and 2, and the coefficient of restitution, determine their speed just after impact. So we know that I like his graphics here. So this is the plane of impact. And this, although I'm going to erase it in a minute, this is the line of impact. So what I'm going to do, I'm going to use both of those and create a x coordinate along that and a y coordinate along that. Now, if I go back and look at the book, these others, if you notice, he gave you the x and a y, and that's the reason I picked this one. This one, he gives you an indication that that's what you want to do. Here's your x and your y. Okay, this one's hitting a wall, an x and a y. So I wanted to pick one that didn't give that. And then I think I don't have, oh, I'm sorry, I do. He didn't say this, he didn't say x or y here. Here he doesn't say anything. Here he says x and y. So he's getting you used to this concept that the impact is occurring along that X line. And so in this one was one of the first ones that I glanced at and saw that he didn't give you that indication. So since he didn't give you that indication, this was maybe there's another one like this too. I don't really know. So what you do is along the line of impact, you can use the coefficient of restitution. Along the plane of impact, or along the Y, if you look at it, I'm going to do this and kind of erase it in a second. So you got B, and you got A, and how should I do this? I guess I could make them hitting each other, and they're sort of going together, but in this one's going this way, this one's going a little bit this way, and a little bit that way. So it has a VY component. During the impact, if I just look at A for a moment, there is a force this way, but there's no force this way. Fy is equal to 0. So during the impact, B doesn't hit A and apply any force along the Y. So because of that, what you'll find out, and you can find that by going back and looking at what we talked about the last time, the velocity of A, or B in the Y direction before impact, I'll say initial, is equal to velocity of A and the Y final, which is after. So, and the reason that is because if you have an object that's moving and you take two particular times and you don't have a force, I mean, let's say you had a force right here pushing on this, you may change its direction this way, but you're not going to change its direction in that way. I mean, you're not going to change its velocity that way, since you didn't push on it or pull on it. And so that gives us a very, very clear approach, because, here, give me a second. I guess I could have just selected all these. So now I'm going to go along the line of impact. And what I'll do is MA, and I'll say AI is equal before impact, and F is equal after impact. Let's see how my battery's doing now. Is it 6? Oh, it's 7. So I've got the system so it'll charge a little bit at a time. So velocity A before impact plus MB BB before impact. Now I could put the forces, integrate F A onto B dt plus the FB onto A dt, but they're equal and opposite, so they cancel each other out, so they're kind of gone. And then what you get, MA VA final plus MB BB final. So you're sitting here looking at this. Let me see if I can turn the screen up a little bit more, since I am charging. Kind of a fine line. Okay. So he tells me 4 and 2. I'll say 4 and 2, 4 and 2, VA final, VB final, which I don't know, VA initial. Okay, that's this one. So all I've got to do, okay, so I've got to break a component here. I think you came in on it. I got, oh, what do I got there? I don't know what that was. Huh? I don't know what happened there. Okay. Now, I guess maybe I could do that. Then I could do this. Just move that to there. Don't know what happened there. I don't know that that's, I don't know the way to do it. Here, I'll just do it this way. So if I compare these two, let's see. I think to myself, this is the way I think sometimes. I'll take this line and I'll roll it that way. If I'm rolling it that way, eventually this angle will collapse to 0. If I'm doing that and rolling it that way, this angle collapses to 0. So this looks weird, but the opposite is 4, 5, and 3. That doesn't make sense. The other way to look at it, let's think about that for a minute. Is that true? I'll have to. Okay, because if I take that thing, collapse it down, yeah, the other way to look at it is this. If I take this line, and then I take this line, it goes this way, and this line. I'm chasing a rabbit. If you let me chase the rabbit. So the angle between this line and this line is the same as that line, because this one and this one go in the same direction, and that one go in the same direction. This means this one has to be, just going to make something up. Say if that's 26, I shouldn't make that up. Here I'll say this is theta and this is alpha. So theta plus alpha. Well, if that's 90 degrees, then this angle has to sit right there. So in fact, I got them backwards with my funny logic there. Okay, so in fact, this angle and this one are the same. And if that's the case, then I have 3 and 4. Now I've got a bunch of junk everywhere. However, if I multiply times 3, I get 9 and 12 and 15. So now I've got velocity A moving, this is the plus x direction, so that means it's moving in the minus 9 plus 2 times velocity of B is coming straight at it, or going in the positive x direction, and that will be 8. So I got my right hand side. The problem is that I don't know this one or this one, and at this point I only have one equation. And so here, I'll go ahead and try my best at how weird. Okay, so if I do that and work that out, so minus 10 equal to 2 VAF plus VBF, and I'm stuck here with just those two until, and this is the key here, this coefficient of restitution only takes place along the line of impact. And so if that's the case, now I should be stating, I should have put a subscript all along here But this is along the X direction. So now, along the X direction as well, I can use a coefficient of restitution. These are labeled as A and B. And so they're sitting here like this. It tells me this is 0.8, and I'm sort of stuck because I don't know this, but I have this value doing this, and I have this value doing that. And so I have the first one, 8 minus 9. VAF minus VBF is equal to, I don't know, if I do that, take 117 times 0.8, or what's my battery doing? Can I increase the, got 9%, so I think I can increase my brightness just a little bit. Let's hit it right there. Okay. So that's 13.6. So now for the first time, I have this equation and that one I can put together. You can do it in a variety of ways. One, I can take this one and copy it down underneath this one. 2 VAF plus 3BF is equal to minus 10. I'm going to monkey with something in a second, but maybe I won't on this one. I'll do it on another one. And so you're sitting here looking at this, then you can add this equation to this one and get another equation. These two cancel each other out, so they don't have anything. 3BAF is equal to 13.6 minus 10, or 3.6. I think I could divide that. 1.2. Okay, so VA final. So it's saying it turns right, so it comes in here at 9. It says it turns around and goes back this direction at 1.2 after the impact. Let's did I have the right masses? Okay, so the A, the bigger, and I got that as a 4 and a 4. I'm just double checking. And then the B is the smaller one, and it's a 2 and a 2. Just double checking. Okay. So if that's the case, and I haven't made a mistake, and if I have, go ahead and tell me. If I put 1.2 right in here, I get VBF is equal to minus 10. Moving that over with the 2, take that, put it in here, put it right there. 1.2. 2 times 1.2, wait, 2 times 1.2? Yeah, that would be, minus 2.4 minus 12.4. VB final. Okay, so it's telling me that thing, the B, is heading away, going back that way at 12.4. This one's going that way at 1.2. So let me organize my thoughts here for a second. So if I were to list these, a VA final as a vector, I'm going to have a component in the I and a component in the J. I'm looking at A. I see 1.2. That is only along the line of impact. For A, though, I actually have a 12 moving that direction. So I still have the 12 before. So if I were to look, okay, so I got 12. So if I were to look at VA initial, it would be I plus 12J. The reason I'm doing this is I want to look at the kinetic energy and play a game here in a second. So what was this? This. Okay, so I got 12 here, and I got 9, but it's going this direction. So I got 9. We got a minus 9. So that's the before and after for that one. The VB initial, oh, I did final here. Final and VB initial, what does it look like? The B only had a component in that direction. So it had a plus 8 and it had minus 12.4. And plus 8. And minus 12.4. And that's I, and plus no J before or after. So those are the two. You know what? I'll tell you what. Here, let's see. Make it better? How about that? Does that make it better? Why is it not doing anything? Oh, this is weird. Okay, so let's try this again. So it's all. Okay. Why is it doing that? Select all means everything. I have no idea why it's doing this. Like that. Now, down here. Okay. This way I can actually see it on there. Okay, now I hit escape. How many times do I have to hit escape? Apparently many times. Look at the keyboard. Battery is dead. Okay. Let's see. No, it's still there. Okay. So I'll check the answer. I guess I can check the back of the book. Let's see. This would be 1589. Okay. Okay. So he has, he has that. You know what I'll do? Instead of trying to remember that, I'll do this. And then Boom, I can make it move around. Okay, so this is what he gets. VA and VB. Okay, hang on. Put it right there. Ooh, it's kind of tiny compared to that. Okay. So first of all, VB2 is the same thing as that. I put a direction on it. He tells us VA2 is that. And what we're seeing is this. However, I think what he's doing is finding the magnitude. Let's just see if this thing will do this. Sometimes it will, sometimes it won't. I get 12.06. So I'm going to claim that those are close enough. And so what I've done is I've found the component version. And the next thing I want to do is I want to know, and this is not part of his part of the problem, but I want to know if I looked in here and found the kinetic energy initial, and then I looked right here and I found the kinetic energy final, what would they be? And yeah, this is still coming. I'll make it big. So the kinetic energy initial is, okay, it's the bottom row. So it's actually, if I look at this speed right here, yeah, I could say 9 squared plus 12 squared square root. That's the speed. Okay, I need space right here. But if you look at that, that should be 15. And let's see, because that was the initial speed. And that's what that is. But if you look at the kinetic energy, it's 1/2 mv squared. So that means that is v squared. So in other words, if I had some speed that was like this, and this was 12, and this was 9, the actual speed is this. And since that you have that square root of the sum of the squares, that would be the same thing as 15 squared square root. But if I'm going to square that and put it right here, then I'm going to end up with that. And so, in fact, that's what I get for the initial v squared. The mass of that thing is, I do not remember. A was the larger one. So A was the larger one. And it was 4, and then you got a half. And then you got another term here that was a half times 2, because that's the mass of this one. And then I get 8 squared. And so if just by chance this thing can calculate that, let's make sure, it's 514. Now there's nothing that at this point, I mean, this is just a basic fact. But for the kinetic energy final, this is for E equal to 0.8. So we should be losing some energy here. And so if I did this and looked at the final state, I'd 1/2 4 times, instead of 9 and 12, I'd have 1.2 and 12. 1.2 squared plus 12 squared plus 1/2 2 times, instead of 8, I'd have that 12.4 squared. Now what I'll do is see what that is, and that ends up being 400 44.64. So we lost some energy going from here to here. So now what I'm going to do is I'm going to say, what happens if E was equal to 1? And so what I've got to do is I got to go up here and let's see, I'll use a purple pen. So I go over here, and I need it to be as thick as I can get it. I'll go over here and I'll copy that, but instead of a 0.8, I'll put a 1 equals to VAF minus VBF over, and that ends up being 17. So then I move that over and I get a VAF minus VBF equals to 17. And instead of that, look at this one. But I still get 2 VAF plus VBF equals to minus 10. Now I can add them together and I'll get 3 VAF is equal to 7, if I did that right. And then VAF is equal to 7 over 3, and I'm not even going to worry about changing that. So if I get a VAF, which one would be easier? If I did that one, I don't think there is an easy one. So I'll take the VAF and stick it right here. And then VBF will equal to, and move that to one side and move the 17 to the other side. Will be 7 over 3 minus 17. I don't want to calculate that. Let's see if it'll give it to me in a thirds. Oh, it will. Well, so I'm just going to stick with that. Now, I hope this works out. It might not. So, all I'm doing with this is calculating the 1/2 mv squared. So, in this case, VA final, which would be off of here, it would basically be equal to, instead of 1.2, 7/3 I plus 12J. VB final is not going to have any component here, and it's going to have all of this coming from right there. So minus 44 over 3 I. So now I'm going to basically do this for E is equal to 1. So I'll say 1/2 4. Okay, I know it's got to be 12 squared there. I don't know where that thing came from. The 12 squared occurs here and here. But instead of 1.2, I get 7/3 squared plus 1/2, 2. And instead of 12.4, I get 44 over 3 squared. This really looks very ugly. I'm not even sure this thing, I think I wrote it okay. And I get 5/14. So in fact, if I have E is equal to 1, I lose no energy between here and here. So then the other scenario would be, what's the worst case scenario? E is equal to 0. And you're not going to drop to 0. The energy is not going to drop to 0. But in this case, okay, so then I got to go up and do this again. But this time I get nothing right there. So this, okay, so here, this is all for E equal to 1. Recopy it over for E equal to 0, and you get VA final equals to VB final. Oops, that looks pretty ugly. Then, instead of this term being that, I mean, I guess I could write it like that. Here's what I'll do. Yeah. Let me get rid of all these extra things. And what I'll do, I'll copy that. But this time, I'll put over here a big fat 0. I'll add that together. 3 VAF is equal to minus 10. So VAF is equal to minus 10 over 3. And then guess what? VBF is equal to minus 10 over 3. But this didn't mean they stuck together, because they're not sticking together because they're glancing off each other. Because what will happen is this one will still have a velocity going that direction. This one will not. So this one will have a velocity like this way, and this one will have a velocity. So a few seconds later, this ball here will move over to the side, and this one will move. But what will happen is this one might move to here eventually, but this one will be sitting right there. And this one will still be going that way, this one will be going that way, and a component that way. But it sounds weird. Okay, that's so ugly. I'm going to have to just go back to it individually. Okay. So I end up with now a new weird velocity will be VAF equaling to minus 10 thirds I plus 12J, and VB final will be minus 10 thirds I, and that's it. So this is the worst case scenario. They don't stick together because they're kind of glancing off of each other. And the final energy there, or you still got the 12 squared, or what is it, minus 10 thirds. It doesn't matter whether it's minus plus 1/2 2 10 thirds squared. It's got to be less than 444, unless I goofed up. And that's altogether possible. 321.3. So you can lose, you can go from 514 to there, but you can't go any lower than 321. So, but if you, again, if you compare those, okay, so they impacted each other. So if you drew them, here's the one and here's the other. A few seconds later, this one might have moved off here. This one's still going to be right here. A few seconds later, this one will be here. So this one right here goes along that path. This one being A or B, I've already forgot. So this one continues along that path. This one basically parallels it on that axis, but it's still running out that direction. So they don't stick together, but they're completely plastic, and they basically come off of each other. And there's a lot of things here you could argue that are not included. You know, first of all, if two objects are coming together, like two tennis balls are coming together and they're moving and they squish, and one is moving the other, you may find it'll spin one up. And so that's not included here. So there's some things like that that if you want to get into the real nitty-gritty fine details, there's advanced courses in physics that cover this kind of stuff. So there are things like that. You can see that if you, like, for example, if you're playing pool, the pool balls are very, very slippery, and they hit the wall or the bumper side, and they generally don't attach with each other. But if you figured out how to, or you wrapped the ball in like a sandpaper and you pushed it off that side, when it hit, it would be spinning like this as it came off that side. So there are things like that that are not included here. So putting in E equals 0, the analysis should have extra components, because if you have E is equal to 0, I would venture to say, as these things compress down and they didn't have a restoration, so that's what's happening, is they're compressing down and they don't have a returning force. So they're compressing down and then they're moving off each other. So technically, that being the case, they would no longer be round. And so the only way a pool ball could happen that way is it would start wobbling down the. So first of all, you got to look at the complete logic of what's being said. It's great to work things, and this is always the case. It's great to have equations and to work them. It's also good to really question every single assumption that's going on there. If you really look at it, you drop a piece of Play-Doh, it hits the ground, it doesn't bounce off, it becomes a little bit flat. You pick it up, part of it's going to be flat. It took all of that energy, took it away. So it's going to change its shape. There's just no doubt about it. Now, I guess you could take a disc and put it on, and we used to have one of those over there. We used to go over there and play that game, where they may still have it over there. It's like a shuffleboard. It has sand around the edge. Y'all know if it's still there? Is it still there, you think? It was over in Doc Bryan. Okay, so they must have done something with it. We used to go there at the end of the class at this period and go find it, because we would take movies on the iPhone and you find out it does exactly that. So one of the things that happens is if these two balls or the two pucks are exactly the same mass, when one hits the other, if that one stops dead and the other moves on, it has the E of 1. If it doesn't, if it continues to move, in other words, you have one ball, it hits this one. So you can make this observation real clear. If this one has, say this is A and this is B, they have the same mass, so you don't even have to worry about this. So VA initial, B initial, which is nothing, is equal to B, you're canceling the mass out because they're the same mass. So this is the MV, sum of the MV. So VA final plus VB final. So if this is equal to 0, you get an equation. Say this is coming in at just 1. You're just going to make it come in. 1 is equal to VA final plus VB final. And then you say, okay, so this is the momentum. So then you look at the coefficient of restitution. If it's equal to 1, you get VA minus VB over VB minus VA. And here you have the initial, and here you have the final. So what you have is this one is a 1, and that one's a 0. So what you see, you know what? I'll just carry the E first. And then what I have is this term, which is a 1, gets put over there. So you get a minus E, VA final minus VB final. If E is equal to 1, you can just say this. Here, I'll do it this way. I'll swap it. VB final minus VA final is equal to 1. You stare at that for a minute, and what you find out, I guess you could just go ahead and add these two together. If you add these two together, you get VB final there are two of those equaling to 2 because you got this and this giving you 2. So what you do is you say, okay, VB final is equal to 1. Okay, great. What's VA final? If this is 1, that has to be 0. If this is 1, that has to be 0. So what happens is the one puck hits the other, it stops dead in its track, and this one takes off. And so we go over there and film that and find out that's sure enough what's happening. I mean, so the concept that E is equal to 1 is not outlandish at all. I mean, you can find that over and over all over the place. That's not that. So maybe next class period, we'll just go over and see if we can find it. I don't know. I mean, I'll leave here if I can remember when I'm leaving to walk over there. Or if y'all want to. So, do they still serve food in that one little area over there? They don't. What's over there? It's just nothing. Oh, maybe that thing moved over there. Is it over there? Yeah, it has. What it has is it's like a long shuffleboard. It's maybe this wide. It's a little table. It's maybe 4 to 5 foot long, and and it has so it doesn't have a shuffle stick. You use your hand, and then what you do is you reach along. So what it's got this little. So if you look at the side view of it, it's got this, and there's sand they put right in here. And this is where you slide the thing across. So you'll reach in there and pull the sand out, put it on the top, and then you put that and slide your piece across the sand. Oh, okay. Well, if y'all, that's a good homework. So that's what y'all should do. So where's y'all? Do y'all have a next class in here or something, or do you have it? So if you don't mind, walk across there and see if you see it. And then if you don't, maybe see it over there, maybe. And then what we'll do is we'll just abandon class next time and go play with it if we can. Is there any pool tables? Where are the pool tables? In the hall? Oh, okay. They moved it too? Oh, okay. Oh, really? You have to bring all your own stuff? Oh, okay. Well, if you could do that, why don't you bring just a regular tennis racket and a tennis ball, play up and down the hall? We used to do that in grad school. Made a few people mad. We also played baseball in the hall. So my roommate was really into the Cubs. So we got in trouble a couple times. But they don't do anything to you. They just scold you until you go away. So we left. So anyway, look and see if you find that. If not, we might go on an expedition next time. I don't know if I like sitting around up here that much. But anyway, you can find direct evidence of that. You can also do that. Now, see, pool is a little bit different because you can do English on a cue ball. If you hit the ball fairly hard so that it goes across the table, it doesn't have time to develop a rotation of the ball. When it hits the other ball, it stops dead. So you've seen people do that before. If you hit it slow, it starts to spin a little bit, and it hits the other ball, and it has that spin, and it goes forward. So you can do stuff like that. You can also spin the ball backwards, and it hits the ball and it returns back. So there are people that can do all sorts of things there. That's harder to check this out because there's too much other factors there. But in that one case where you had the sand across the disc is flat, so it's not rolling like that. It's just sliding across that sand. And so one of the things we did one time, we went in and put rubber bands around the thing and watched it. And then we saw that, in fact, you can reduce E down by doing that. And somebody else did double-sided tape on it. You never got them to stick together, but you can get double-sided tape that's real thin. You can also get some that has a foam piece in between. And those are like, you can go to Walmart, and those are to hang pictures on the wall. You just take the double-sided tape, it's got a little foam on it, and then the double sides over there, you stick it on the wall and it stays there. So you can do all sorts of things to that to adjust that. So if we find that table, we'll go do that. So I guess I'm done. I don't know. I think somebody's out there for status. Or just maybe I was imagining it.